This webcast talks about the energy of satellites. A satellite is always moving around a central body. So it has a tangential velocity, and that means that it always has kinetic energy. The reason that the satellite moves around the central velocity is because there's a centripetal force. That's the gravitational force that the central body is exerting on the satellite, pulling it back toward the center of that central body. Therefore, the satellite is in the gravitational field of this central body. The satellite always has gravitational potential energy. The total energy of the satellite equals the sum of the kinetic energy plus the gravitational potential energy. In this figure on the screen, we're showing a man-made satellite moving around the Earth. So here, the Earth is the central body that's exerting the gravitational force on the satellite. That central body, which is the Earth, is the larger mass. The satellite, which is the object that's moving in the orbital path, is the smaller mass. That concept of smaller and bigger mass is true for any satellite system. So for example, the Earth is a satellite that moves in a slightly elliptical orbit around the Sun. So the Sun is the central body, it's the larger mass. The Earth is the satellite, it's the smaller mass. The total energy of a satellite is constant. And that's true whether the satellite has a circular orbit or an elliptical orbit. The reason that the energy is constant is because the satellite and its central body represent an isolated system. There is no interaction with another external system, so therefore there's no way for energy to be transferred in or out of the system. In this page, I'm showing an energy conservation diagram for an example of a satellite in circular orbit. So in a circular orbit, the satellite is always at the same orbital radius, right? It's always at the same distance from the central body. Therefore, its orbital velocity is constant. So the kinetic energy, the gravitational potential energy are always constant. There is no change. Position A, the distribution of energy, looks the same as at any other position around that orbit. So you can see that the change in energy is zero. When we talk about satellites, there is a different reference point for zero gravitational potential energy than when we're talking about objects close to the surface of the Earth. For satellite systems, the reference point where gravitational energy is zero is defined as an infinite separation. When the satellite and the central body are at a distance of infinity from each other, then there is no gravitational potential energy. EG is zero. As they get closer together, the gravitational potential energy becomes more and more negative. It decreases. So one important thing to understand is that the gravitational potential energy is always negative for satellites. It's always negative. Here are the equations that can be used to calculate the kinetic and gravitational potential energy and total energy of a satellite in circular orbit. Remember, in a circular orbit, the orbital radius is constant. And so kinetic energy is always equal to the universal gravitational constant, G, times the product of the masses, divided by 2 times that orbital radius, r. Sometimes the radius may be given to us as a combination of the radius of the central body plus the altitude of the satellite. And so R would be the sum of the radius of the planet plus the altitude. Notice that kinetic energy is positive, but if you look at the formula for gravitational potential energy, that's always negative. There's a negative in the formula. Eg equals negative universal gravitational constant times the product of masses divided by the orbital radius. If you compare these two equations, you can see that the magnitude of the kinetic energy is always 1/2 the absolute value of the gravitational potential energy. So if you know one, it's fairly easy to find the other. Also, the total potential energy, the total energy of the satellite, it equals the sum of the kinetic energy plus the gravitational potential energy. And so it's always negative as well. It's negative g times the product of the masses divided by 2 times the orbital radius. If the orbital radius changes, then the amount of energy in the satellite changes. As the satellite moves closer to the central body, in other words, the orbital radius r becomes smaller, then the kinetic energy increases and the potential energy gets smaller. And the reverse happens if the satellite moves further away from the central body. If it moves further away, it slows down, so its kinetic energy becomes smaller. But by becoming further away, its potential energy actually increases, right? It's being lifted higher away from that central body. It does take an increase in energy to lift a satellite into a higher orbit, and you can find that amount of energy by looking at the change in the total energy of the satellite. So the total energy of a satellite increases as the orbital radius increases, and you can find the energy required to move the satellite to a higher orbit by looking at the change in the total energy. Remember, the change in total energy is the final total energy minus the initial total energy. I'm showing that here in this energy conservation diagram, and this would be for something in circular orbit, but at position A, we're at the lower orbit. We've got a certain amount of kinetic energy, a certain amount of gravitational potential energy. When you move it to a higher orbit, the kinetic energy decreases, but the gravitational energy increases quite a bit. So there's more energy at position B than there is at position A. That energy had to come from work that was done on the satellite Earth system. For example, maybe that work was done by rockets that fired and exerted a force on the satellite. So that work that the rockets did is equal to the change in the total energy. Let's solve a problem where we look at how much energy it takes to move a satellite to a higher circular orbit. So we have a 175 kilogram satellite moving around the Earth in a circular orbit. Initially, its orbital radius is 7 million meters, but we want to move it higher to an orbital radius of 7.5 million meters. So to find the energy required to change that orbit, we have to look at the change in the total energy. The formula for total energy has a negative sign in it, and so I think it helps simplify the math if you factor out the negative gmm over 2 from both of the total energy equations, and then you've got that the change in energy is negative gmm over 2 times the inverse of the final radius minus the inverse of the initial radius. When you plug all these things in, you can see that the change in energy, it is a positive value. Okay, let's talk about the energy in elliptical orbits. In an elliptical orbit, both the distance between the satellite and the central body and the speed are always changing. So that means that the elliptical satellite, its kinetic and gravitational potential energies are also always changing. But the total energy, that's the sum of the kinetic and the gravitational potential energies, that total energy is constant. And it would be given by negative g times the product of the masses divided by 2 times the semi-major axis. This equation for total energy looks very similar to the equation of the total energy for a satellite in circular orbit, but here the distance that's important is the semi-major axis instead of the orbital radius. And just one final example, looking at and using the energy of a satellite in an elliptical orbit. So we've got a situation of a planet orbiting a star. We're given the period as 7.78 million seconds, and they're giving us a semi-major axis. The semi-major axis is the clue that tells us this is an elliptical orbit. They're asking the mass of the star. So in this case, the star is the central body. That means it's the big mass, the uppercase M. And then they're giving us the total energy of the planet. Notice the total energy is negative, right? The total energy of a satellite is always negative. And they're asking, what's the mass of the planet? Well, it helps to make, for us to understand that in this case, the planet is the object that's moving around the sun. So it is the smaller mass. I'm going to make a list of the things that the problem is giving me. Period T, semi-major axis A, the total energy. I'm looking over these units to make sure they're standard units, and here they are, so I don't have to convert anything. My strategy is going to be to use Kepler's third law to find the big mass, right, the mass of the star, and then I'm going to use the equation for the total energy of the satellite to solve for the smaller mass, the mass of the planet. So for that first question, finding the mass of the star, I take Kepler's third law, I rearrange it to solve for the mass of the central body, the big mass. I can plug everything in and get that mass. And then for the second question, finding the mass of the planet, I know that the planet here is the satellite, so it's the smaller mass. So I take the total energy of the planet and rearrange it to solve for the smaller mass. And notice that I do get, of course, a positive value for that small mass because the energy, the total energy was a negative value.